Now, first order reaction, so that's zero order reaction. Now, first order reaction is where the reaction rate depends on the first power of concentration of a single reactant. So in this case, the concentration of the medicine determines the rate at which the forward reaction occurs. Okay. Examples include absorption, distribution, and elimination rates of medicines, and including microbial death kinetics. I don't know what level you're supposed to be introduced to the use of antimicrobial compounds, where you'll also be taught about how antimicrobial chemicals are used in hospitals to ensure, to ensure that or to reduce cross-contamination with microorganisms, right? But all of that, this first order reaction is mainly what is described when we're looking at the use of, or the applications around using these antiseptics in cleaning or cleaning the hospital environment and killing bacteria. Now, the rate of reaction in a first order reaction is directly proportional to the concentration of the reacting substance and can be expressed with this formula, right? As the concentration changes over time, you have it can be described as constant K times that change in concentration. If concentration of reactant X is A, this is an assumption, and we want to do a little bit of modification, so we can use this formula for calculations, right? Derive T half-life and other parameters. So we assume that if the concentration at the beginning of the reaction is A, at the beginning, when time T is 0, and if the amount that has reacted after time T is denoted by X, then the amount of X remaining at time T will be A minus X. I hope that's clear. It will be the amount at the beginning minus what has, what has changed, what has reacted, right? Now, we can rewrite this equation as the change of concentration over time equal to constant K times A minus X, which is the concentration as it varies over time, right? And then manipulating this information a little, we have this equation 4, which is change in concentration of X divided by A minus X is equal to minus K over as time changes. Now, integrating this equation, you will have the natural log of A minus X minus natural log of the concentration at the beginning of the reaction is equal to minus KT. And finally, changing this back to the log, you have log A minus X is equal to log A minus KT over 2.303. Now, this is very important because this is a straight line graph, or is a straight line graph equation. And when we apply it to our plot again, for example, if you have a medicine, right, and introduce it into a system and then watch it react over time, and then you take samples, for example, every, let's say you administer paracetamol to a patient, and paracetamol, is distributed according to first order kinetics, right? Over 6 hours, you take aliquots or you take samples from this person's blood, right? And you try to get the concentration of paracetamol in the person's body, right? And then you plot log of this concentration change as over time, right? against time, you'll find out that you get a straight line graph from the initial concentration as it tends to go down to 0, right? The slope of this graph is minus k over 2.303. Very important to note. The slope of this graph is minus k over 2.303. Now, rearranging that equation, we can also get equation 6, right? Now, the unit of k, which just describes our k, right? It's from just knowing what time in the equation and the initial concentration we start with, and of course, how that concentration has been degraded at that time t, you can get the k, that's the rate of reaction for that substance that you're doing experiments on. It can also be used to predict how fast the medicine will be, will be cleared out of the person's system, or how slowly that medicine will be distributed across this person's body who has taken the medicine that we're describing, right? Now, a very important parameter for describing how medicines are distributed or eliminated in a person's body, eliminated, is the t-half. That's the time required for 50% of the drug to be moved out of the person's body, right? That's to be eliminated out. And you can calculate it as follows, right? So from our t-half, that's 50% of the time, right? To get to 50% of the concentration. Of course, that's just like saying that's just like saying A is 100% and A minus X, that's when it gets to 50%, right? By the time we bring T as a subject of the formula, take K down there, right? By the time you finish, once you simplify that equation, you'll be left with our T half is equal to 0.693 over K. So this formula is important for finding out the time at which half of the concentration of the drugs would have been eliminated. Very, very important for you to note. Now, in manufacturing, the time it takes, for example, for medicines that have been manufactured to also degrade by 10%. Most of the drugs that we manufacture, about it's important to identify when 10% of that medicine is degraded. It's important for determining the shelf life. That number is important for determining the shelf life of the product. So manufacturers are always, trying to identify factors that can contribute to, speeding that reaction up. So one of the ways to do it is also using this. If the drug decays by first order statistics, first order rate of reaction, then you can use this equation. Of course, just substitute for concentration again. Remember, we're looking at the time it takes for it to degrade by 10%. So we're looking at 100 over 90. And then by the time you simplify this equation, you get 0.104 over K. Sorry, this should be 0.104 over K. Or you can simplify it. If you know the T half of K, we already said that K is 0.693, right? So our K will be 0.693 over T half. If you substitute it into this equation, right, you will get your T 10% is 0.152 multiplied by the T half, right? Very important. I was going to put out a question here, but I also realized that our time will not permit. So I'm going to put in a few, a few questions into the classroom before the weekend, so you can, test run what you understand from this class.